Hello, welcome everyone. Today our speaker is Masatoshi Suzuki from Tokyo Institute of Technology, and Professor Suzuki is going to talk about an inverse problem for a class of canonical systems with no indivisible intervals. Professor, thank you very much for being with us today.
Yes, thank you very much. And
okay.
First of all, yes.
You can start whenever you are ready.
Yes, okay. So first of all, I would like to thank Professor Ajat Setinkaya for inviting me this seminar of inverse problem. So and since my main research field is number theory, so my knowledge of function analysis and differential equation and other analysis is quite limited. So any comments or suggestions or questions are very welcome. And yes, this talk consists of 3 parts. The first part is a brief introduction to the canonical systems and the direct and inverse problem. Then in the second part, we state the result for our inverse problem for the canonical system, and we also compare our method with the result of the method of Crane for the inverse problem of the Crane string, and the third part is the results for more general setting. And if we have a time, we talk about this part. So now let's start the first part for the brief introduction to the canonical system. So the theory of canonical systems generalize exponential function from the perspective of Fourier analysis. More precisely, it is the fair-linear theorem, which characterizes the space obtained by the Fourier transform of L2 functions on some finite intervals. Anyway, we start with the most simple case of the canonical systems. So, for finite interval I, from 0 to a with finite a, and unknown function u of tz on I times c, and taking values in the Coulomb vectors of length 2, we consider the initial problem for the linear system of the linear first order system, this one. And if we write the component of u as a and b, then this system is equivalent to the pair of these differential equations. And this pair of differential equation is equivalent to this pair of second order differential equations. So under this initial condition, we find that the solution of this system is equal to cosine. The vector consists of cosine and sine. So from this, we obtain the exponential function by the linear combination of the components of the solution of the system, this first order system. And general canonical systems are generalizations of this kind of system with initial condition. And so, yes. So let h of t be a measurable function defined on the interval I from t0 to t1, and taking values in the space of a real 2x2 symmetric matrix. For such matrix valued function h of t, we consider the linear first order system associated with this matrix value function parameterized by the whole complex number z for a known function u of tz on I times c and taking values in the column vector of the length 2. This type of the system is called canonical system on interval I if the h of t is non-negative definite for almost every t in the interval I, and h of t is not identically 0 on any interval or any subset of I with a positive Lebesgue measure. And thirdly, each component of the matrix H of t is locally integrable. In other words, each component is integrable on any compact subset of I. And for canonical system, the matrix value function H of t, this part is called the Hamiltonian of the canonical system. Okay, this is the general definition of canonical system. And as the name of canonical system, suggests, several classical ordinary differential equations are reduced to canonical systems. For example, we put the Schrödinger equation for potential for integral potential and one space variable with the spectral parameter z. For this Schrödinger equation, let alpha and beta be the solution of the homogeneous equation with normalization of Wronskian is equal to -1. And we define u of z by the column vector consists of y and its derivative with respect to x times the inverse of the matrix consists of alpha, beta, and their derivative. Then we find that this u of xz satisfies the canonical system associated with Hamiltonian h of x with written as alpha square, beta square in the diagonal, and alpha beta on the anti-diagonal. So in this way, a canonical system and the classical Schrödinger equation is related to each other. And we also have other examples. The Dirac equation or the string equation are also reduced to the canonical system, but we omit it today. Now, so like this canonical system is in this sense, a canonical system is canonical.
We have some troubles with Wi-Fi. Maybe we'll wait.
What? Okay. Yes, then we define E of tz by using the component of the solution. Then this function belongs to the Hermite-Wheeler class HB for every fixed t in the interval. The function E in the Hermite-Wheeler class is a generalization of exponential function. The function in the Hermite-Wheeler class is the entire function satisfying this inequality in the upper half plane. So the absolute value of E of z bar is less than the absolute value of E of z. And E of z does not vanish on the real line. Sometimes we don't assume this non-vanishing of E of z on the real line, but today we include this in the definition of the element vector class. So actually the exponential function exponential of a z with positive a satisfies this condition. So in this sense, the function in the element vector class is exponential, the generalization of exponential function. So the summary, in summary, for given Hamiltonian H, solving canonical system associated with H gives the function E belonging to the element vector class. So as a result of direct problem. Okay. So from this result or in the direct problem, the following question naturally arises. So does any function E in the element vector class come from the some Hamiltonian or canonical system? This is the problem. This is today's inverse problem. So, but the answer to this inverse problem is known to be yes by the result of the MZ Crane in 1954 for the results for the inverse problem of strings, and the result of Louis Dublange around the 1916 dealing with more general case of canonical system. So Dublange's result for this inverse problem is as follows. So for function E in the element vector class, there exists the Hamiltonian H defined on some interval C, where C may be the finite or infinite. And taking values in the 2x2 positive or negative definite matrix, and there exists a family of the function in the element vector class parameterized by this interval, such that the E0 is equal to the given E in the element vector class. And if we define AT and BT by a half of ET plus ET sharp and BT by the I/2 times ET minus ET sharp, the where the ET sharp means in just f of z bar and its bar. So complex conjugate of f of z bar. This is the definition of some notation sharp. And if we define the function AT and BT from this function, then they satisfy this canonical system attached to this Hamiltonian on this interval and C. And thirdly, this initial condition holds for pointwise. So in other words, this limit holds for any fixed z and w. This limit condition is a generalization of the initial condition before. So in the previous slide, we consider this kind of initial condition, but if the solution satisfies this initial condition, then this implies this limit behavior. So, but of course, this limit behavior does not reach this one. So, in such a sense, this limit behavior is some generalization of this initial condition. Anyway, so the branch proves that for every given function E in the element Wheeler class, there exists a Hamiltonian and family of functions in the element Wheeler class satisfying the canonical system recovering the original E. So although this result solves the inverse problem for canonical systems, the Boulanger's result does not provide a way to explicitly determine the Hamiltonian H from the given E. So in other words, the Boulanger's result guarantees the existence of this kind of Hamiltonian, but it does not give the explicit form of the Hamiltonian. So, but an explicit method for constructing the Hamiltonian from the function in the element Wheeler class has at least one number theoretic interest or application. It is let z of s be the Riemann z function defined by the series sum over n equal 1 to infinity and n to the minus s when the real part of s is less than 1. And we also define the Riemann c function by Riemann z of the z function times gamma of s over 2. So this is the usual gamma function, and pi to the s over 2 times s minus 1. So the Riemann z function extends to the meromorphic function on the all complex plane and holomorphic expressed for the simple pole at s equal 1. So the Riemann c function is as one of the entire function. So for the Riemann z function or the Riemann c function, the Jeff Lagarius proposed in 2005 that the Riemann hypothesis, which is one of the Millennium Prize problem for Crane Math Institute, is true if and only if Ec of z defined as c of 1/2 minus iz plus a derivative of c of 1/2 minus iz is this belongs to the element Wheeler class. So from this result of Jeff Lagarius, the following question naturally arises. So what's the Hamiltonian H corresponding to this entire function if the Riemann hypothesis is true? And also, can the conjectural Hamiltonian H be used to for studying the Riemann hypothesis? And someone considers other questions. Anyway, so the following main results are obtained from studies conducting to answer these questions, but we don't touch this topic any further today. Yeah, but anyway, so this is my motivation to the solution of inverse problem for the canonical system. So now we go to today's main result. So we state the result after a little preparation. So to explicitly recover the Hamiltonian H from the function in the element Wheeler class, to explicitly recover H from the function E, we introduce the following 4 conditions for function E. So in the following, we don't assume that the E belongs to the element Wheeler class. So E is just a function satisfying the following 4 conditions. So the first condition K1 is that E of z is an entire function and satisfies the E sharp equal to E of minus z. This was E sharp in the previous notation. This condition sometimes symmetry in the theory of canonical system. Anyway, the second condition is that there exists a real valued continuous function k of x defined on the real line, vanishing on the negative real line, such that absolute value of k of z is bounded by exponential with some positive constant c as x to the infinity, and the Fourier transform of k of z as equal to the ratio of E sharp over E of z. And this integral formula holds for complex number z with imaginary part of z is larger than c. So under these two conditions, the map k of t that maps a function h of x to the integral with the kernel k in the second condition defines the Hilbert-Schmidt operator on the L2 space on -infinity to t for every fixed positive real t. So this integral operator k of t plays an important role in today's method of the constructing the Hamiltonian in the inverse problem. So anyway, so in addition to the above two conditions, we consider the following two conditions. The third one is that the case is continuously differentiable outside the discrete subset lambda of the real line, and the derivative of k belongs to the locally integrable function on the real line. But this third condition is some technical one, but the following fourth condition is very important. So the fourth condition is that there exists the number tau as a positive or infinite, such that both +1 and -1 are not IM values of the operator k of t on the space L2 minus infinity to t. For every fixed t larger than or equal to 0 or less than tau, this one. So in other words, for any fixed t in this interval, the operator 1 plus or minus k of t is invertible. So these four conditions may look very artificial, but the set of function E satisfying all of the above four conditions is not empty. In fact, we get many examples of such function E from number theoretic Z functions. Anyway, so for E of Z satisfying the above four conditions, the Hamiltonian of a canonical system is constructed as follows, so that it is the Hamiltonian in Dublanger's result if a function E belongs to the Hermite-Villard class. Okay. So now we state that we need one more revision. So hereafter we assume that the function E of Z satisfies all conditions in the previous slides, and we define function small m of t by the ratio of the fluid form determinant of 1 minus k of t and 1 plus k of t. And using this function m of t, we define the matrix value function h of t as a diagonal matrix with m square or reciprocal of m square on the diagonal. then the square of m of t is a continuous function, continuous and positive real valued function on the interval minus infinity to tau. Tau is the number in the fourth condition. So therefore, this h of t is a Hamiltonian on this interval, consisting of continuous function without no indivisible interval. So I did not explain what is an indivisible interval. So the open interval J in I is called is H indivisible if H of t equals equals a matrix cosine square of cosine theta and square of sine theta and cosine theta sine theta and cosine theta sine theta times a scalar function h of t for some theta and scalar valued function h of t. So in this case, the interval J is called H indivisible interval. So in this case, these functions are the continuous function. What? So this Hamiltonian don't have H indivisible intervals. Anyway, the solution of the initial value problem, here the A of Z is defined by this one, and B of Z is defined by this one, and yes. So the initial value problem, this one, for canonical system on this interval associated with this Hamiltonian, recovers the trivially recovers the original function E, because this initial condition suggests that the solution satisfies this equation. And so the solution of the direct problem for the canonical system associated with this Hamiltonian is constructed as follows. So we consider the pair of integral equations like this for unknown function bar phi plus or minus in the L2 space, in this L2 space. Here on the right hand side is belong to here. The right hand side belongs to the same L2 space by our condition K1 to K4. So using the solution of this integrated equations, we define function capital plus or minus t of x by 1 plus or minus and integral of this 1 plus 1 times the kernel k, which appeared in the second condition. And we define the function a of tz and b of tz by the Fourier transform of this capital phi or capital phi plus or capital phi minus times e of z and e of z, and this the simple factor. And this integral actually converges if the imaginary part of z is sufficiently large, but we can prove that the function a of t A of tz and B of tz extend to entire function of z for every fixed t in this interval. And these functions, the vector consisting of these functions solves the initial value problem in the previous slide. So this one. So now we get to and by using this function capital V plus or minus, the function m of t the function m of t are defined as the ratio of fluid form determinants is equal to the special values of these functions. Okay. Anyway, so the theorem 1 and the theorem 2 are obtained relatively easy by partially differentiating the integral equation for capital bar phi or capital phi. I did not mention that if we define the function capital phi by this one, this function capital phi plus or minus satisfies this integral equation. Yeah, this satisfies this integral equation. Anyway, so by differentiating this integral equation, we can relatively easy to prove that this satisfies the canonical system associated with this Hamiltonian. Anyway, the difficulty of today's impulse problem lay in showing this third result. So the third result is if we assume that function E satisfies K1 to K3, so the first three of condition, and E belongs to the Hermite-Wheeler class, and moreover, this ratio cannot be expressed as a ratio of two entire functions of exponential type. Then the fourth condition holds for tau equals infinity, and this limit behavior holds as t tends to infinity. So here, tau infinity is equal to tau. So this limit behavior holds pointwise. But from this first result and the third result, we see that the matrix valued function h of t with diagonal m of t square and m of minus of t square is nothing but the Hamiltonian in the branches result. So to show that this is the Hamiltonian in the Lagrange result, this part is the most important. So now we complete stating the method for the solving of inverse problem of today, but we mention one more result. So although it's not identical, not directly related to the inverse problem, but it has some number theoretic interest. So whether or not E belongs to the Hermite-Wheeler class does not affect our construction of H of t and the solution A of t and B of t. So from these facts, we can determine whether the function E belongs to the Hermite-Wheeler class or not, according to the properties of the integral operator K of t. So this is the fourth result. So assume that the function E satisfies all of four conditions, K1 to K4. And in K4, we can take tau is equal to infinity. that is 1 plus 1 minus k of t invertible for all positive t. Then we find that the function e belongs to the Emmett-Wheeler class. And this follows from the theorem 3. So this result has a number theoretical application, but the speaker does not know if it has an application for function analysis or other area of analysis. Okay, so now we then compare the above way of the inverse problem with the classical Acquain's method for inverse problem of the Crane string. So the Crane's method for solving the inverse problem for Crane string can be stated in terms of canonical systems as follows. Suppose that suppose that a function e belongs to the Emmett-Wheeler class, satisfies this condition, and this integral formula holds for some measure tau on the positive real line. Yes. So the function e appears in the right-hand side. So in general, further conditions are necessary to justify the following discussion, but they are omitted for today for simplicity. Anyway, to find Hamiltonian h of t attached to this e, we first introduce the transfer function phi of t. This is quite different from our function phi of t, but we follow the Crane's notation. Anyway, so we define the function phi of t by this integral. So integral of 1 minus cosine of t root of lambda over lambda with respect to this measure. And where this is a function on the positive real line. And for this function phi of t, we consider the family of integral equations parameterized by t. So this one. So the function phi of t is the kernel of this integral, and the function q of xt is unknown of this integral equation. And so using the solution of this integral equation, we set function p of t by the square of q of tt over q of 0, 0. Then, so we obtain the Hamiltonian of the inverse problem for E is equal to the diagonal matrix consists of P of t and reciprocal of P of t on the diagonal. In this way, the Hamiltonian h of t is recovered from the spectrum measure t like this. So t was appeared in this formula. So the solution of canonical system associated with H is also obtained from the solution Q of t, but we omit it today. Anyway, as above, today's method and Crane's method are quite similar in the sense that constructing a Hamiltonian H using a solution of an integral equation coming from the given function E. But they are technically different, including the form of integral equation for kernel of integral equation. So today we use the function k of x satisfying this free integral formula. But in Crane's method, the kernel is coming from this Fourier integral formula. On the right-hand side is someone think very similar, but someone think not very similar. Anyway, and also now today we consider the pair of integral equation, but in the current method, the integral equation was a single. But it also includes the second derivative of this formula. But in today's method, we just have function k of n itself. So now we complete the proof of we complete the statement of the theorem and the comparison with the Green's result. So I heard from the organizer that the talk will be 45 to 50. So how many time I have? How many time I have for today?
We have 20 minutes with the question session.
Okay, 20 minutes.
20 minutes with the questions and everything.
Okay. So yes, so we will talk just the 5 minutes. Okay. Yes. So we go through some more general cases. So in the previous result, we assume that 4 conditions, but we will relax the condition in the first and second condition. So in the first condition, we can remove this condition, and in the second condition, we remove the condition for the real values. So anyway, if we remove this part, we modify the operator k of t as the kernel is the same, but we put a complex conjugate of f of y on this integral. Then the Hamiltonian h can be obtained from the given e in the same way as before. So we consider the same integration before, and using the solution of this integral equation, we define the capital P plus or minus by this formula. So as well as the operator k of t, we also put the complex conjugate in this integral formula, and we also define the function h of t by using the special values of this function. So as in the theorem 2, this was given by the ratio of Fluid-Holm determinant, but we cannot give such an expression for the Hamiltonian of this case. And anyway, we also define the function a of t z and b of t z by the same Fourier integral formula as before. Then we find that a of t z and b of t z are extended to entire functions for every function t in this interval, and the vector consisting of a of t z and b of t z solve the initial value problem. This one, so the a of t, a and b is defined as this one for given e of the canonical system on this interval associated with this Hamiltonian. So this is a generalization of theorem 1, and the theorem 3 is generalized as follows. So assume that the function e satisfies the relaxed version of the first and second condition and the third one, and assume that e belongs to the Hermite-Wheeler class, and the ratio cannot be expressed as a ratio of 2 entire functions of exponential type. Then as well as the theorem 3, the K4 holds for tau equals to infinity, and this limit behavior holds point-wise. So from this theorem 5 and theorem 6, this is a Hamiltonian in the branches result. So finally, we outline the proof of theorem 6, and as mentioned before, the theorem 5 is obtained relatively easy by partially differentiating the integral equations for phi or capital Phi. So the difficulty is raised in the proof of the theorem 6. So the proof of the theorem 6 is done by using the theory of the branches space, which is the Hilbert space of entire functions satisfying some nice conditions. So all subspace of the branch space are generated by entire function E, which is defined to be this one, are represented as this formula. So this is the usual L space, and K is an integral operator with kernel function K of T, and F is the Fourier transform. So we can prove that all the branch subspace of the branch space having this formula. So then we let the vector xz of T in this space which satisfies this integral condition. For all f in this space, so this is the space in this part. No, sorry. Then the limit behavior in theorem 6 flows from this integral formula. Yes. So by proving this integral formula, we can relatively easy to prove that this limit behavior. So now I want to complete. I want to finish today's talk. So for details, please see my paper in the series of these ones. Yes. So thank you for your attention. Thank you very much.
Thank you very much, Professor Suzuki, for the nice talk and for being with us today, despite the time difference, because it's very late there in Japan. So anyone, any questions or remarks for Professor Suzuki?
Can I say some words?
Yeah, of course.
You see, at the beginning of your talk, you suggest us the statement of the inverse problem. Roughly speaking, of course, it's roughly. The statement is the following. You construct a part of monodromy matrix vector. I call it monodromy vector. Of course, it's not correct, but for simplicity, I will call it monodromy vector. So the inverse problem is formulated as follows. Given the monodromy vector, construct the Hamiltonian. But this inverse problem is not good because the specification of this monodromy vector doesn't uniquely determine the Hamiltonian. And then you formulated this problem, and then you immediately forgot about this problem and study completely different one. You take concrete monodromy vector and show that it's possible to construct concrete Hamiltonian with this monodromy vector. But in this case, it's natural to, from the beginning, to suggest another statement of the problem, to choose the concrete subclass of Hamiltonian and solve this problem in this class. Otherwise, it looks not natural. It's my opinion.
Ah, yes. Thank you.
Okay.
Okay.
Okay. So
Yeah.
Any other questions or remarks?
I have a question. In the second part in your construction, you used a function denoted by m. Does that has any connection with the classical Weltitschmark m function, or
A function. Yes.
this m function does that have any connection with the Weltitschmark m function, or
What is the question?
a Weil m function in the classical setting? Maybe I should say do you use Weil m function in your construction, or does this m function have any connection with that? That's what I
Sorry, I cannot catch what is the question. So
Professor
the
Hatinoğlu
question is
asked
about the function m.
the
yeah.
function m. Okay, Burak, please go on.
Okay. In the classical setting, a function called Weil m function, or sometimes Weltitschmark m function.
Weil m function. Okay.
Yeah. Do we have
Yes, but
any connection in here?
there is no connection with the Weil m function. We just write this m of t, so it is confusable. But this not a connection with the Weil m function. Sorry for that. Yeah.
Thank you.
Okay, any other questions or remarks? I guess no. Okay, then we can call the day. Thank you very much for the talk again, Professor Suzuki, and your time and your cooperation. And everyone, thank you very much for being with us today. We are going to see you again in 2 weeks.
Thank you, Professor. See you next time.
Thank you.
Thank you
Bye.
very much.
Bye.
Bye.